Hello, I'm Dr. William Schlosser, Washington State University, School of the Environment. This is my classroom.
Ecosystems operate through ecological processes under the influence of the constraints of the physical environment. These processes give understanding of the potential each landscape has to grow and establish. Throughout our entire ecological study, we will discover how nutrients begin their genesis at the level of geological substrate. It is plants which take up these nutrients after they have been converted into usable matter, dissolved in water, and pulled by roots to give life to growth. The entire process is enabled by the primary energy source of this planet, the sun. Taken all together, we begin to understand this study of ecology. First, we will take a look at the history of global climate. We back up about 540 million years to discover where that thermometer has settled, from icehouse to sauna, and begin to understand climatic cycles and how life responds. The climate of the Cambrian, 540 million years ago, is not well known. It was probably not very hot nor very cold. There is no evidence of ice at the poles. By the Ordovician period, 520 million years ago, mild climates probably covered most of the globe. The continents were flooded by the oceans, creating warm, broad, tropical seaways. About 440 million years ago, the late Ordovician was an icehouse world. The South Polar ice cap covered much of Africa and South America. The climate in North America, Europe, Siberia, and the eastern part of Gondwana was warm and sunny. By 420 million years ago, coral reefs thrived in the clear sunny skies of the southern arid belt, which stretched across North America and northern Europe. Lingering glacial conditions prevailed near the South Pole. Generally dry conditions prevailed across much of North America, Siberia, China, and Australia during the early Devonian about 400 million years ago. The early Permian climate was globally cold, an icehouse planet from 280 million years ago. Much of the southern hemisphere was covered by ice as glaciers pushed northward. Coal was produced in both equatorial rainforests and in the temperate forests during the warmer interglacial periods. Then, 252 million years ago, the planet got warmer as the Permian epoch initiated. Though the southern ice sheets were gone, an ice cap covered the North Pole. As the Triassic period continued, the interior of Pangaea was hot and dry. Warm temperature climates extended to the poles. This may have been one of the hottest times in Earth history. Rapid global warming at the very end of the Permian may have created a super hothouse world that caused the Great Permial-Triassic extinction, a 15 million year event that happened during the latter part of the Permian period, 299 million to 252 million years ago. Approximately 99% of all life on Earth perished during this Permial-Triassic extinction. Moving forward into this Jurassic period, the interior of Pangaea was hot and dry. Polar regions were warm, even during the winter. This warm climate continued for the longest period in geologic history. The Pangaean mega monsoon was in full swing during the early and middle Jurassic. The interior of Pangaea was very arid and hot. Deserts covered what is now the Amazon and Congo rainforests. China, surrounded by moisture-bearing winds, was lush and verdant. During the late Jurassic, about 175 million years ago, the global climate began to change due to the breakup of Pangaea. The interior of Pangaea became less dry, and seasonal snow and ice frosted the polar regions. During the Cretaceous, about 100 million years ago, the global climate was warmer than today's climate. No ice existed at the poles. By the late periods of the Eocene epoch, global climate was warmer than today, but it was cooling on a global scale, initiating around 34 million years ago. Ice had just begun to form at the South Pole. India was covered by tropical rainforests, and warm temperate forests covered much of Australia. During the early Oligocene, ice covered the South Pole, but not the North Pole. Warm temperate forests covered northern Eurasia and North America. Even though this was a cooling period for the planet, it was about to get colder. The climate during the Miocene was similar to today's climate, but still, it was warmer than we see today. Well-defined climatic belts stretched from the pole to the equator. However, there were palm trees and alligators in England and northern Europe. There have been 5 or 6 major ice ages in the history of the Earth over the past 3 billion years. It has been in the warming cycle only since about 11,700 years ago. Even today's warmed climates, we are still cooler than we have been as a planet since the Permian epoch about 290 million years ago. Keep your attention on these numbers, 17 million years ago through until about 14 million years ago. We will focus on significant events happening as flood basalts spilling over parts of eastern Washington, Oregon, Idaho, and Utah. Another metric to ponder is the study of life on Earth, to recognize that our ancestors have been around for about 6 million years, but the modern form of humans only evolved about 200,000 years ago. Seems that puts us in the cadre of Ice Age dwellers, breaking out of the igloo to catch some sunny rays on those sandy beaches.
If you want to know how your here got to be where it is, you first have to know where land comes from and how it behaves. And for a long time, we just didn't know. The idea that the continents could actually move was first proposed in 1912 by German scientist Alfred Wegener. He spent years traveling the world collecting geological and fossil evidence to argue that all of the continents were once connected. Wegener was the first to propose the idea of continental drift, and the notion was so outlandish at the time that it basically cost him his career. And part of why no one accepted Wegener's theory was that no one in his day had ever seen the bottom of the ocean. Until the mid-20th century, most scientists assumed that the seafloor was basically featureless, like a giant wading pool. But in the 1950s and 60s, pioneering researchers like Marie Tharp and Bruce Heezen began studying the bottom of the ocean, and they found that there was an enormous mountain range running right through the middle of the Atlantic. Eventually, more of these undersea mountain ranges, called mid-ocean ridges, were found in all the world's oceans, and they were all volcanically active. These ridges, it turned out, are where the seafloor is made. Geologists realized that these mid-ocean volcanoes are actively creating the rocky material of the seafloor and spreading it outward in a process called seafloor spreading. But what the sea gives, it also takes away. Far from these ridges, at the edges of continents, researchers also found huge trenches. And here, the dense rocks of the seafloor dive below the lighter rocks of the continents in a process called subduction. So the denser, heavier crust that makes up the seafloor, known as the oceanic crust, moves under the lighter land masses, known as the continental crust, just a few centimeters at a time. And as oceanic crust sinks back into Earth's interior, it begins to melt and mix with the mantle. So seafloor spreading and subduction are the two key mechanisms behind plate tectonics, the theory of how giant chunks of Earth's crust, called plates, move around the surface.
We just looked through the concepts of climate, specifically in terms of global temperatures. Now we take a similar calendar walk to observe how here became here. This land we stand on, has it always been at this place of our planet? Our walk observes the supercontinent of Pangaea, looking back about 650 million years. Late Precambrian supercontinent and our ice house world. This map by Dr. Christopher Scottis illustrates the breakup of the supercontinent Rodinia, which formed 1,100 million years ago. Staying with Dr. Christopher Scottis to 540 million years ago, animals with hard shells appeared in great numbers for the first time during the Cambrian. The trilobite was widespread in the oceans of the world. The continents were flooded by shallow seas. The supercontinent of Gondwana had just formed and was located near the South Pole. Keep your eyes on that little red dot. This is Chicago long before it became the Windy City. Watch where it blew in from. By 458 million years ago, during the Ordovician, ancient oceans separated the barren continents of Laurentia, Baltica, Siberia, and Gondwana. The end of the Ordovician was one of the coldest times in Earth history. Ice covered much of the southern regions of Gondwana. At 425 million years ago, Laurentia collides with Baltica, closing the northern branch of the Iapis Ocean and forming the Old Red Sandstone continent. Coral reefs expanded, and land plants began to colonize the barren continents. Ahead to 390 million years ago, the Devonian period with the early Paleozoic oceans were closed, forming pre-Pangaea. Freshwater fish were able to migrate from the southern hemisphere continents to North America and Europe. Forests grew for the first time in the equatorial regions of Arctic Canada. By 356 million years ago, the early Carboniferous and Paleozoic oceans between Euromerica and Gondwana began to close, forming the Appalachian and Vardiscan Mountains. An ice cap grew at the South Pole as four-legged vertebrates evolved in the coal swamps near the equator. Ahead to 306 million years ago, the late Carboniferous witnessed the continents that make up modern North America and Europe had collided with the southern continents of Gondwana to form the western half of Pangaea. Ice covered much of the southern hemisphere, and vast coal swamps formed along the equator. At 255 million years ago, vast deserts covered western Pangaea during the Permian as reptiles spread across the face of the supercontinent. At the Great Permian Triassic extinction, 99% of all life perished. Dinosaurs started to spread after about 251 million years. By 237 million years ago, the supercontinent of Pangaea, mostly assembled by the Triassic, allowed land animals to migrate from the South Pole to the North Pole. Life began to diversify, and warm water fauna spread. Rushing ahead to 195 million years ago, the end of the early Jurassic, South Central Asia had assembled. A wide Tethys ocean separated the northern continents from Gondwana. Though Pangaea was intact, the first rumblings of continental breakup could be heard. By 152 million years ago, the Great Permian Triassic extinction. The supercontinent of Pangaea began to break apart in the Middle Jurassic. In the late Jurassic, the Central Atlantic Ocean was a narrow ocean separating Africa from eastern North America. Eastern Gondwana had begun to separate from western Gondwana. At 94 million years ago, the Cretaceous epoch saw the South Atlantic Ocean open. India separated from Madagascar and raced northward on a collision course with Eurasia. Notice that Australia was still joined to Antarctica. By 66 million years ago, the impact of a 10-mile-wide comet caused global climate changes that killed the dinosaurs and many other forms of life. This is the KT extinction, and all games changed. By the late Cretaceous, the oceans had widened, and India approached the southern margins of Asia. The early Eocene from 50 to 55 million years ago, India began to collide with Asia, forming the Tibetan Plateau and Himalayas. Australia, which was attached to Antarctica, began to move rapidly northward. As we entered the Miocene era about 23 million years ago, global temperatures signaled the oncoming global ice age, which witnessed the rise of mammals. By 20 to 14 million years ago, Antarctica was covered by ice and the northern continents were cooling rapidly. The world had taken a modern look, but notice that Florida and parts of Asia were still flooded by the sea. By the time 18,000 years ago arrived, the last glacial maximum was named. The Earth is fully in its icehouse climate mode. There is ice at the poles. The polar ice sheets expands. The last expansion of the polar ice sheets took place. We are now entering a new phase of continental collision that will ultimately result in the formation of a new Pangaea supercontinent in the future. Global climate is warming because we are leaving an ice age, and because we are adding greenhouse gases to the atmosphere. It is these events happening simultaneously that we see as climate warming. On one hand, it is the natural process of leaving a global ice age as we approach warmer trends. And on the other hand, we are adding carbon dioxide to the atmosphere, which warms the climate. A truly meaningful scientific exploration is to determine how much of the global climate warming is from anticipated cycles established over the past 650 million years, and how much is from gases like CO2 emitted from purely anthropogenic sources. Investigating this is a truly meaningful examination. The lithosphere is the outer solid part of the Earth, including the crust and uppermost mantle. The lithosphere is about 100 kilometers thick, although its thickness is age-dependent. Older lithosphere is thicker. The lithosphere below the crust is brittle enough at some locations to produce earthquakes by faulting, such as within the subducted oceanic plate. The crust or surface of our planet is broken into large, irregularly shaped pieces called tectonic plates. The plates respond to movements in the Earth's center to slide past each other along transform plate boundaries, pull apart from divergent plate boundaries, or push together at convergent plate boundaries. 100 million years ago, the Pacific Ocean shorelines were found in western Montana, north-central Idaho, and through parts of Nevada and California. The superterrane feature is an exotic delivery along the Farallon Plate active 100 million years ago, and has become a fixture of the continental batholith. By 70 million years ago, the Baja BC exotic, it is presumed, was guided into eastern Oregon, Washington, and northern Nevada. These exotics reside in an accretionary wedge where the ocean shoreline interface is actively subducting below the continental plate. Volcanic processes are actively building up the Rocky Mountains. Although no volcanoes are found here currently, those volcanoes had an active life of about 5 million years each. The dead volcanoes stopped activity long ago, leaving the granite beds that fed the erratics delivered to Washington and Idaho during the Missoula glacial floods. We will get into these more soon. By 50 million years ago, the exotics delivered by the Farallon Plate had formed Vancouver Island. Subduction since that time has shifted south of the Straits of Juan de Fuca to form Washington's Olympic Peninsula. This accretionary wedge has delivered, stacked, and compressed oceanic exotics into this region as the lithosphere continues to subduct below the continent, providing fuel for the andesitic volcanoes of the Cascade Mountain Range. Subduction of an oceanic plate dipping below the continental plate makes large volumes of magma. Subducted basaltic plates are forced into the lithosphere and eventually into the asthenosphere under pressure and heat to melt and rise as they feed magma chambers. This forms batholiths of granite and diorite. Cones of hot and pressurized magma are formed until volcanoes blow. We live along the Pacific Ring of Fire and know the active volcanoes forming the Cascade Mountain Range from Washington through Oregon and even into California. In subduction zones, sediments and hydrothermally altered organic crust, which together form part of the subducting slab, contribute to the chemical composition of lavas erupted at the surface. The entire extent of the region that today is called the Olympic Peninsula is a conglomerate of sediment-covered materials that were scraped off the eastern-moving oceanic Juan de Fuca plate under the North American continental plate, beginning at the Cascadia subduction zone deformation front. We continue to look at the ocean side of the Pacific Northwest to see the texture of this Pacific plate as it begins its forced dive under the continental plate at the Cascadia subduction zone. Materials on the seabed are scraped off the dense subducting plate to form an accretionary wedge. These wedge materials constantly pile up one against the other, ultimately causing an uplift to create things like Mount Olympus. The entire Olympic mountain range is non-volcanic. Accretionary wedges formed near the shallow end of the subducting slab as pieces of oceanic crust and marine sediment get plowed into a wedge by the overlying plate. This is the formative process when large inorganic materials are delivered from the ocean plate to the continental shelf. Although trilobites are signature organisms of the Paleozoic, first appearing in the early Cambrian, they were prominent features of marine biota. That was 485 to 400 million years ago. But here they were, near the crest of Mount Olympus in 1972. A photo makes them look large, but really, they appear as fossil imprints about the length of my thumb, embedded in basalt layers poured onto what became the Juan de Fuca plate. Meshed to the east in the accretionary wedge, they ultimately were found residing here at 7,000 feet above sea level. While relatively infrequent, the megathrust earthquakes have a fairly well-documented return interval of about 400 to 600 years. Researchers believe that strain within the locked zone of the subduction fault is currently building, and as it does, the likelihood of a major subduction earthquake event increases. More common earthquakes occur within the subducting oceanic crust, or within overlying continental rocks, as the February 28, 2001 Nisqually earthquake with an epicenter near Olympia, Washington provides a fairly recent example. Rock strength is related to composition and temperature. Rocks near the surface of the Earth behave in a brittle manner. Crustal rocks are composed of minerals, like quartz and feldspar, which have high strength, particularly at low pressure and temperature. At a depth of about 15 kilometers, we reach a point called the brittle ductile transition zone. Below this point, rock strength decreases because fractures become closed, and the temperature is higher, making the rocks behave in a ductile manner. At the base of the crust, the rock type changes to periodite, which is rich in olivine. Olivine is stronger than the minerals that make up most crustal rocks, so the upper part of the mantle is again strong. But just as in the crust, increasing temperature eventually predominates. At a depth of about 40 kilometers, the brittle ductile transition zone in the mantle occurs.
A radical shift in volcanism and tectonism begins with the outburst of flood basalts at 17 million years from rapidly north migrating vents along the boundary between accreted terrains and the North American craton. The basalt outpouring is immediately followed by a pulse of silicic ignimbrites. This burst in basalt plus rhyolite volcanism is the onset or resurgence of the Yellowstone hotspot under the continent. While subduction-related volcanism persists in the Cascades Arc, migration of North America across the Yellowstone plume creates a succession of calderas that become younger to the east along the Snake River Plain to reach the Yellowstone caldera. We use a cross-section of the subducting plate and hotspot interaction in which part of the Yellowstone plumehead flows up the base of the ancient, thick North American plate at about 17 million years ago, resulting in the flood basalt outpouring. As the North American plate pushes west, the Yellowstone track migrates east. As the Juan de Fuca slab steepens and rolls back, backflow and upwelling of the Pacific mantle around the receding slab simultaneously creates westward migration of silicic volcanism across southeastern Oregon. To view what was happening tectonically in map view during those 17 million years, let's again rewind volcanism to 17 million years to superimpose the simplified regional plate motion. Block faulting of the Basin and Range extensional province was ongoing as the Cascadia forearc rotated clockwise about a pivot point in northeastern Oregon. At about 5 million years, bimodal basalt rhyolite volcanism migrated to the edges of the Basin and Range province. As the Juan de Fuca plate dives beneath the North American plate, the Pacific plate is dragging the Sierra block of California, which is pushing on the Oregon Coast Range, that in turn pushes on the Washington crustal block. The stalwart Canadian mountains resist. The youngest basalts are concentrated along the trace of the older age-progressive rhyolites in the northern Basin and Range. In recent time, volcanism became focused on the Cascades Arc, segments of which have distinct character.
These are the flood basalts spread across eastern Washington, Idaho, and Oregon. Columbia River basalts are the world's youngest flood basalt province. A hotspot chain of eastward younging volcanoes we call the Yellowstone Trend. We live in a volcanological wonderland. We will explore the 15 to 7 million year old Columbia River basalts. The Columbia River Basalt Group is a large igneous province that lies across parts of western United States in the states of Washington, Oregon, Idaho, Nevada, and California. During the Middle to Late Miocene epoch, the Columbia River flood basalts engulfed about 163,700 square kilometers, or 63,200 square miles, of the Pacific Northwest, forming a large igneous province with an estimated volume of 174,300 cubic kilometers, 41,800 cubic miles. Eruptions were most vigorous about 17 to 14 million years ago, when over 99% of the basalt was released. Less extensive eruptions continued through about 6 million years ago.
Is it true that these bedrock layers in eastern Washington are lava rock? They are. Is it true that those lava rocks, these flood basalts, came from Mount Rainier? They did not. When Mount Rainier or any cone-shaped volcano in the Cascade erupts, they make andesite lavas or rhyolite lavas or dacite lavas. These are different kinds of chemistries. And these are basalts. Look at this map. Look at how much of the Pacific Northwest has this thick pile of basalt lava. It's nothing to do with the Cascades. Let's get that out of our minds right now. Mount Rainier, Mount Hood, I don't care. Nothing to do with tonight's talk. Is it true that these giant lava flows, and they are giant, some of them traveled 300 miles, some of them are more than 100 feet thick. Is it true that those lava flows are unusual? Sure. I mean, they're bigger than the lava flows you see in Hawaii or Iceland, where we're going to go tonight, by the way. But is this the only place in the world that we have these kinds of lavas? No. No. There are flood lavas like these in Siberia. There are flood lavas like these in India. Well, okay, fine, but ours must be the biggest and the best, right? I mean, you know. No. We are small potatoes compared to these other flood basalt areas, and we will look at the volumes tonight as well. Amen. This is just a big pile of lava surrounded by stuff that's not lava, essentially. And in this cross-section, we can see this stuff here that's just buried beneath all this lava. So if you are a geologist who loves all this old rock, all these metamorphic and granite rocks, and they tell all these old stories of Washington, you hate the Columbia River basalt lavas. If you are a person who loves all these rocks or loves all these rocks, you're not a fan of these flood basalts because the flood basalts have buried almost everything. Here's one place that the lavas have not buried everything. That's called Steptoe Butte over by Pullman. That's a mountain peak that kept its chin up above all of these lavas. But most of those mountains are still down there. They're just under, and I'm not making this up now, 2 miles of lava. In some places, more than 3 miles of lava. So I've heard on field trips geologists who love these other rocks talk to this as a big giant cow pie. They're not a fan of our flood lavas, our great lavas of tonight. But some of you came into town, you had a beautiful meal downtown, so you don't want to talk about cow pies, and I understand. So let's not call it a cow pie, let's call it a German chocolate cake. How about that? Okay? Brown, rock, brown. So this is the cake.
The Columbia River Basalt Group is the youngest, smallest, and one of the best preserved continental flood basalt provinces on Earth, mainly eastern Oregon and Washington, western Idaho, and parts of northern Nevada. Rock quarries have ample sources to mine these flood basalt rocks. This one is located between Washington State University campus and the University of Idaho campus, along State Highway 270. Far below this flood basalt layer is a layer of quartzite, deposited here 100 to 50 million years ago. But look to the top. This is the Los Soils layer which overtops Arpalouse Hills. Those soils came here as another significant event shaping these lands. We will give specific attention to that quartzite substrate, formed when this was oceanfront property. Sediments, sandstone, compression, and uplift were all forming these hills where the accretionary wedge was happening. Those flood basalts from 17 to 14 million years ago covered this topography. At Kamiak Butte, only its head and shoulders are still seen today, but it is overtopped by the Los Soils we will explore soon. This portion of the story involves glaciers and winds. Dr. Christopher Scottis revealed a glacial ice cap over North America during this last ice age, 2.56 million years through about 11,700 years ago. That ice cap was given new visualization by Douglas Merrick. We will keep coming back to this event in the next lecture. First came the formation of this landscape when we were oceanfront property, 50 million years ago, when these lands were being compressed and uplifted. Then came the flood basalts starting about 15 million years ago. The period of flood basalts ended about 7 million years ago. Then, about 4.5 million years later, glaciation started to cover the planet, at about 2.56 million years ago. Through much of this period, the Earth's northern and southern regions were covered by kilometer-thick glaciers. The southern boundary line in our area of Washington was seen along the northern edges of Washington, Idaho, and Montana. It is important to recognize that the Pleistocene was a series of real ice ages, separated by relatively short interglacial periods. The Pleistocene started 2.6 million years ago and lasted until the termination of the Wishtashil glaciation about 11,700 years ago. In geologic time, that is like happening earlier today. But this glacial retreat happened as a new significant entry was found, a flood of glacial melt waters to scour eastern Washington landscapes. Discovery of how flood debris is seen at the top of Kamiak Butte is the next mysteries to solve. We will do that in the next lecture. Throughout this series, seek to understand how the geologic substrate of lands you manage were shaped, where they came from, and what nutrients they possess. In natural resource ecology, we want to understand the availability of nutrients for plants to access and grow. These substrate materials inform what is hidden below. So next, we explore the soils found on top of it all.